Good evening, everybody. So let us start our lecture tonight, and only a few students I see. But today our lecture will be short, an hour should be fine. And today actually we will discuss the most difficult task of the semester. Maybe this is the most difficult, and to me it is most boring and uninterested. So looping deletion in a red black tree. Okay, I will just give you some heads up, and then there are some videos on YouTube. I found at least one or two that I will refer you. That was whenever you have cool brain, you will have 2 or 3 sittings, and you please watch the video, an hour video, but it will take you 2 hours. Whenever even you review my lecture, if you don't understand, then please give pause and then rewind, okay, then it will be clear. Otherwise, in one sitting, in one lecture, it may not be sufficient for many to cover this, okay. I will try my best to give you some heads up. So what did we discuss in our last lecture? Remember that we discussed we are discussing red black tree, right? A red black tree is a binary search tree. Remember that, right? It is a kind of, definitely it is a self height balanced binary search tree. So it always maintain all properties of a BST, of a binary search tree, and additionally there are some other its own properties. So there are 5 properties that we discussed. Let us recall quickly. These are the properties for red black tree, right? Any node either row red or black, root is always black, okay, leaf is black, and this is the most important, most troubling one, the last two. If a node is red, then both its children are black. So in other words, it says, we said that, sorry I did not highlight it last time, there are no 2 consecutive nodes like parent child node that are red, because this is same thing. It says if a node is red, then both child are black. That means no child is red. That means there is no consecutive nodes in a simple path from root to starting to beginning, at any situation there is no consecutive to root. I think for visual looking, this is easy to check whether it is a red black tree or not. And the last one is that in all path the number of black nodes is same, right? If there are 4 black nodes in all path, then that needs to be 4 black nodes. And we saw that while we do insertion, we maintain all of these rules, right? And in order to satisfy all of these rules, sometimes we did coloring, rotationing, right? Recoloring. Okay, and remember that one thing, when we discuss our red black tree insertion, we went from bottom to up. We saw that it's sometimes its own color, changes own color. If that does not satisfy, it changes parent color. If that doesn't satisfy, we also looked at its uncle color, sometimes grandfather color, and it will go from bottom to up all the way until it completes, right? So tonight we will discuss a little bit about deletion. So just get us an idea. I will give you only some assignment work for deletion, but in the test I will not ask you to write the entire algorithm, but I will give you some part in the test, not intermediate, medium level complexity, not too much simple and not too much complex. Okay. I remember when I was a student like you, I lost my attention whenever I started this. And honestly, I did not find any application yet. Maybe I did not do that kind of job that uses red black tree. So if I would get a chance to work on it, then maybe I would get more interest on it, right? So I did not get an interest, so I think it is boring for me. But we need to cover it. Okay. So as we say that in insertion case, we need to check color, right? There are some rules, right? AVL rules and then BST rules. And then here in delete operation, first of all, we need to remember this is a BST. So for delete operation of BST, it maintains all properties of BST. The BST deletion operation, let me recap BST deletion operation. Okay, I will recap BST deletion operation for. Okay. Let us think that this is. Let us take a slide, make a slide. It says grouped. And check on group. Give me 1 second, please. We want to an example. Let us take it. This is just BST, so we need to make it black. So let us go to the algorithm where it is deletion and then put it out there. BST deletion. Very good. Okay, let us do this. Okay. So we will learn red black tree deletion. Okay, but red black tree deletion is more like it start with a BST deletion, as a red black tree is a BST, right? but sometimes we forget that red block tree is a BST. So let us recap quickly how, oops, color black. So 4 is root. Okay, how do we want to delete a node that is, for instance, 6? Okay, but let us do it simple. For instance, let us delete 3. Okay, so in BST, in order to delete a row, a node, actually we do not delete, actually it is from memory. Okay, what we do, so like linked list, we do in linked list we do not delete a node, we just unlink it, right? Delink it, we close, delete the link. So here, so actually in BST we do not delete a node. Actually what we do, we change its value. So every node has its value, right? So we are working with value 4, 3, 2, 1, 2, 3, 4, 5, 6, 7. For instance, if you want to delete simply, for instance, this node with 3, you know that in a BST, all of these are called leaf level leaf level nodes, right? So for all of these, there are 2 null nodes. Remember that there are 2 null nodes, right? So the 2 null nodes are like for A, for A, there are 2 null nodes, like this is null and this is null. So put n means null. Okay. So for all of these, there are 2 nulls. 2 nulls over here, 2 nulls. I'm not drawing all, but you know this. All nulls, all nulls. Okay. For instance, if you want to delete, it's easy to delete this this leaf level node. So for instance, if you want to delete 1 or 3, what we just do, we replace this value. We check, for instance, we want to delete the node with value 1. So we start with root and we check that 1 is less than 4, so we come left side, and say 1 is less than 2, so we come to left side again, and then we will get this point, we will get this value. And then what do we do? So for instance, then this value equal to, we replace by this. So target value equal to this null value, right? Target value equal to null. So that means this, it gets null. Value is null. So whenever it gets null, then it no longer can contain anything. Nothing can contain anything. So it automatically it gets deleted. So then this becomes null. It gets deleted. Okay. Similarly, if you want to delete 3, then it will check same process. 3 is less than 4, they will come left side, but 3 is greater than 2, so they will go right side. And then any of these value, either this null root, right side, right child, or left child, no matter, we will replace this value, so it will get null. And then if once it is get null value, then it cannot have any child. That means dead. Okay. And this way is simply we delete a leaf level node. Okay, now how about if we want to delete a node that is not root level, but leaf level. Okay, it can be root, okay, or it can be anything, any node. So except this 1, 3, 5, 7, 9. Let us think that, for instance, we want to delete either 4 or 8, 4 or 6. So let us think that we want to delete this 6. We want to delete this. This is our target. Not going to delete. How do we delete? There are 2 ways. Okay. So since it is not in leaf level, so it has branch, right? It has child. It may have only single child, or it may have child and then grandchildren, great grandchildren. Again, right? For instance, this side it has child and then grandchild, and but only it has only this side is grandchild. So deletion process it calls two ways. One is takes is left predecessor. This is called predecessor. So deletion can happen two ways. One way W1 is way one is taking the actually predecessor is left always, left predecessor. Or another way is that taking the right, success is all of the right successor. So what is predecessor and what is successor? Successor is the lowest value from the right side. It is the lowest value from the right side. And similarly, now I understand predecessor, it is the highest value or highest value value from the left side. You can do either way. Okay, so let us do this way. The book says this way. People usually do this way. This is more popular. So what is the lowest value? Successor is what is the lowest value from the right side? What is this? 7, right? It is 7. Value is 7, right? So then this 7 value we got, right? This 7 value, this target value is replaced by this 7. So 7 goes here. Okay. Now let us see that it maintains BST, this part, right? 7 is greater than 5, less than 8 is okay, and then but we have duplicate 7. Now we know that how this 7 will be deleted, because in a BST we cannot have duplicate element, right? So this 7 will, how can we delete? A few minutes ago we discussed how can we delete this 7. A few minutes ago, that is the very basic one we discussed. How did we delete 1?
Take a null value. Hit the null value.
Yeah, put a null value from either side. This null value put over there, so it will get null, right? So once it gets null, automatically it cannot have any leaf, any null. So it's now it is 7. Now this actually, what did we delete? We did not delete 7 actually. We deleted 6, right? You understand? 6 actually not deleted, is overwritten. Node value is overwritten. So memory address can hold only one value at a time. So 6 will be replaced by 7. So 7 is gone. Similarly, what if you want to delete it? If you want to delete 4, how did you do? But 5 would go into the 4, right? 5 is the successor of this right side. Then instead of 7 over here, 5 would go over here. And 5 would be root. This is the way we delete in BST. Okay, maybe I forgot to cover this in when we discussed BST, but now is the time that we read. Does anyone has any question? Were you in last lecture?
Yes, I was.
Okay, you got your answer. Try, please give me back.
Cool.
I inserted this grade in your grade book, so please have a look. If there is a mistake from my side, please let me know. Does anyone has any question about this? Okay, so it is simple, and let us keep in mind we need this first of all to delete in a red black tree. So now if we come back to red black tree deletion, in addition to this, in addition to deleting a node, it also need to maintain its color, especially the last two properties, number 4 and number 5. And it also need to maintain the number of black nodes in each path. So that is the complexity comes arise. Actually, there are more than six for if black. Actually, 8. Actually, there are 8, 9, 10 special cases. 8, 9, 10 cases for deletion. So unless you have the only thing to this is the only thing you can do, then you can give concentration. Otherwise, it's difficult to give concentration about this. Especially in the test time, I will not give you that much hard time. Okay, but I will give you homework. Okay, in the assignment, then you need to spend some time. So the assignment I gave you is a illustrate. Take some data, a random data set. Okay, maybe at least 10, so that it covers all of the cases. Okay, you can study together, but do not copy something. Take a different data set. Okay, then you will be understanding then how to do that. Okay. So okay, the steps are the first to regular BST deletion. We just recap those how to do that and fix any violation of red blast property that may result. So this part is easy, but this is the most difficult part. To maintain, to check, or to validate all of the properties, right? Okay. Now let us spend some time to understand this. Okay. First of all, okay. So the book algorithm says something like this. So like BR deletion, this is it comes as a method. T is the tree and G is the new node. G is the node, target node that you want to delete. So the first topic says if left, this is left of G. Some book says G dot left. Okay, same thing, left of G or G dot if equal to null nil T, that means it is nil, or if right child equal to nil. That means, for instance, if it does not have any child, okay, then whatever value you will do, then we discussed in last time. So then let me come with y equal to predecessor D8 is on G, and then I counter Z. Okay. Let me give an example with that. It will be easy. You see that the algorithm is it did not come in one phase. So this is the first phase and this is the second, and all together, and this is this one is the complexity one, is fix up. Okay, and then fix up is more complicated. Fix up is more complicated. Here fix up start over here and it ends here. It is also two pages. In the book you can see in one page. Okay, so let me go with an example. Start with a simple example, then we will see. Okay, what the algorithm says. The algorithm okay, for instance, if you want to delete a node, and if our node is red, and if that is the simple case, if that is the leaf level node and it is red, okay, then delete it right there. It's easy. Okay, and we know that how do we delete it? Error. We just discussed, right? In BST, deleting its leaf level node is just is replace this value by its nil value. Okay, then just replace this one this deleting 10, okay, so by n. Okay, then it has already 9 already has leaf side, this side nil. So okay, and this side nil and this side nil is okay. Then 10 got deleted, right? That is the simplest one, but life is not easy that much. Okay, now if we want to delete a node that is not red color, that is black color, that is the most difficult one. Deleting black color is difficult one. Okay, now but if I so we will go the difficult part later. So algorithm, in the algorithm it says go to the difficult part later, but go to the simple part. For instance, if so, okay, so if you want to delete 10, right, there is no problem. Okay, delete 10 because the number of red and black is same, black node same for all cases, and there is no red black issue. Okay, but if this red node is not the leaf level node, then second steps complexity. For instance, we want to delete 8. Okay, then how do we delete 8? So here, remember one thing about that, we are performing two tasks simultaneously. One, we are deleting from a BST, and another we are maintaining color, right? So here, in order to delete 8, so 8, now recall BST deletion. How did we delete 8? Either by successor or predecessor, right? So here then number 9 is the successor, right? So number 9 will go over here. Okay, 8 will be replaced by number 9. Okay, number 9 will be replaced. by 9. But what about its color? Huh? So color will be either so 8 was already red color, right? And 9 was black color. Okay, so then whatever its color. So then if we wanna make it so then okay, so again let me go first. So 9 will come over here, and then later this 9 will be replaced by null, right? Okay, this will be replaced by null. Okay, so then we have 8 is replaced by 9. So now look at that. In order for this is simple case, there are 3 black nodes, right? So in order to maintain 3 black nodes, so 1 2 3 1 2 3, and 9 is coming. So one thing that we are just replacing value, not changing color yet, right? So that means we put 9 over here as a red. Now let us check that does it maintain the last property. Yes, there is no issue, right? You see 1 2 3 1 2 and then say 3, and this will be deleted, so don't forget about that. This no longer exists. Okay, so now it is fine. So deleting red node is not that much bad. Okay, so if it is left label node, then delete it right away. But if it is not left label node, then upper level, then delete it, then replace it by its predecessor. Okay, and then for instance if it may happen that this is a very large branch, it has many sub branches, then again you need to replace, for instance here this after moving 9 from here to there, we got 9 is the leaf level, right? So it was easy. But if there is another branch or sub branches over here, we need to process the same thing. Okay, we need to move from target from here to here, and this will be already replaced by its successor. Okay, so this is the process that is start from the up and go down. You understand this way? So I'm telling that if there are more branches, not null branches, other branches that are not null, there are other values. Okay, there are other values. Then this 9 will be replaced by this value, right? Successor value, right? On the right, successor value. Okay. Okay. So replacing a red node is simple. Okay. Now let us go to the complex situation. It says that number 1, it says if left node is nil or right node is nil. Now let us come this way. What does this mean? For instance, if you want to delete something 5 7 let me make it 8. and then back is 7. So the first one is says if this one is null or this one is null. This is or, not and. Okay, then this is our target will be, then g value it goes to y. This is y and this is our g value, and then g value this goes to this, goes over here, as we saw in our demo over here. Okay, and actually what it says, no, I don't like this algorithm. Actually, what is actually, it should be here, it should mean that if there is this is nil level, if this is nil, is it nil? Okay, it's nil, that means if it is root level, it is leaf level. Okay, then put the leaf, replace this leaf, go up, and either go up, then it will solve either this way or actually this way. Okay, and else y. Otherwise, if there are other sub branches like this, like this, as we saw in our previous demo, if there are not null, there are sub branches, then what we'll do, it will find the tree successor. Okay, it is for this is g, and successor of this tree successor will be this value, right? The lowest value from the right side, this value will go here. This is the successor. That this algorithm, this says this part. Okay, and then again now it says if left side of y equal to nil, then do this the right, or do this blah blah. There are a lot of operation. Let me, instead of going this algorithm line by line, I want to go just with some demo examples. Okay, and then I will tell you that I will show you a video link I found in pretty good video. That's good video, but you can watch that on. We have a few minutes, then we'll discuss. So this part, especially the problem is over here, the deletion delete fix up. So now fix up mainly comes for the black node, deleting black node. If y is a black, then we could have violation of red black properties, right? Okay, now check either property 1 is okay. Okay, so if it is black, then this is the only one root, one element. It may be, if it is only root, then delete it, there is no problem. Property 2, if y is the root and x is red, then go to the root has become what I want to discuss. This is the 5 properties. Let me go. What is 5? So fix up, it says this one. Okay, the algorithm it takes, why it is there are actually 6 conditions, 6 different states. If, but why it says 4 cases, actually there are 6 cases. If it is black, if a node is black, then it may happen 6 cases, different cases that it may happen for the fix up. Okay, now let us take a break and then I will go this. Okay, okay, what I'm gonna do, Okay, it says 8 cases in total, 4 of which are symmetric to others. Then this is 4 symmetric to others. This is 4 plus. That should be 8. How did they make a 6? So this says 8 cases, but I know there are 6 cases. Let us see. Okay. So what is our target? We want to delete a node that is black. Okay. So the black also, think about that. A black node can be the leaf level node, right? Or it can be any intermediate node, right? Black node can be a leaf level node, or it can be any intermediate level node. Okay. For instance, as we saw that if how did we do that for, let me think, 2, 4 and 1. I'm trying myself. For instance, all are black. This is root, this is leaf, this is leaf. If you want to delete this one, remove this one, then it will violate. This side will be, okay. So now let us think about this one. Before we go through this fix-up algorithm, the main algorithm, for instance, before it says, let us think about that. If we have a very simple red black tree like this, 1, 2 and 4, or 1, 2 and 3, okay, maybe simplicity 1, 2 and 3. So is it a red black tree? Yes, right? Even though all nodes are black, right? Still it is a red black tree, right? It's a red black tree. How about if you want to delete either 1 or 3? A black node, you want to delete a black node, right? Okay. So for instance, if you want to delete 3, we know that 3 has null type leaf, right? Null type child. So this null will go to 3. This will be null. Now, is it a BST now? Is it a red black tree now? So then now it becomes 2 and 1. on a looper. Is it a red black tree now? How? Tell me please.
I mean, it doesn't violate anything, does it?
What decimal violates? And let us check the number 5. Last properties.
Yeah. So.
Does it maintain last property?
What's the number 5? All paths to the leaves have the same length, which is true. Is that the one?
Yes.
Yeah.
So this path has 2. Black is 1 and 2. And this path has black only 1.
But there's no leaf there.
Huh? There is. It has empty nail. It has nail. It has nail. So you want to consider nail? Then if you consider nail, then 1, 2, 3. 1, 2, 3. But if you then 1, 2.
Well, then that could never be a red black tree because.
Yes, it is not a red black tree. This is why I added 2.
So then, like a 2-node tree could never be red black because the root has to be black and all the leaves are black. Oh no, the leaves would be considered nodes, right?
Yeah.
So then the 1 would be red. Okay.
So then now, in order to make it red black tree, what do we need to do? We need to do some recoloring. So which one we do recolor? Is sibling. It's sibling, right? We're going to recolor is sibling. So that what we will do, we will recolor this one. Now is it a red black tree? Now yes, right. So after recoloring, yes. Does anyone has any question? Adam, is okay? You didn't understand? Everybody understand? So now it is a red black tree. So what we are getting that in order to delete a black node, okay, even we saw the red node, especially black node, we need to go to down. We need to check or recolor downward. But remember that when we wanted to insert, we went to upward. Its uncle color, its parent color, its grandparent's color, we recolor upward, right? And then for deletion, we go downward, right? For instance, that may happen that it has some other branches, you know. So for instance, let me now, it is time that we can go to this example. How did you put that on? We wanted to delete 6, for instance. What even for simplicity we want to delete 5? So just deleting 5 is easy. If you want to delete 5, okay, then 5, deleting 5, so then deleted 5, then in that case this side, this is no branch, so it is fine. Okay, if you want to delete 7, leaf level, okay, then it is fine because it will not maintain any more branch. But if you want to delete 6, if you want to delete 6 or even 9 is easy, okay. So 9 will be after 10, then it will be easy, okay. But for instance 6, we are entering into the complex situation, okay. If you want to delete 6, then what will happen? The 6, so it will break the 5th property. So how do we delete 6? We say that it will replace by 7, right? The value will be replaced by 7, its successor value, right? From the right side it takes right 7, this value will be replaced by, so even, let me take this one. Six. Replacing black note. For instance, if you want to replace this one, delete this one. First of all, this 6 will be replaced by 7. Value will be replaced by 7, right? Okay. Then let us see. I am not sure that it will make that one 7, and then 7 will be replaced by nil. And now let us see what happens. And 1 2 3 1 2 3 1 2 3 1 2 3. No, it is good in that case. There is no problem. Yes.
Isn't there a path that's too short if you go 4, 7, 8 and then to no?
4 7 8 9.
Yeah, but if you go the other way, then it's only
4 7 5.
4, 7, 8.
You cannot stop. You need to go all the way. Leave from root to leave.
Yeah, but there's also a leaf on the left of it,
Where?
right?
This will be deleted. In null will be deleted.
Yeah. So then there will be a leaf there.
No, there will not. This no longer this will exist.
The fact that there's two paths, the things that doesn't matter.
So then this is 1 2 3 3 black note. This is 1 2 3. This is 1 2 3 and this is 1 2 3. It's okay. Right? You are asking this question or something else? Okay. So in that case, it is good. Okay. But the fix up is for other cases, not even like this much simplification. Let us go to the fix up algorithm. Okay. Here it says if W is, we want to delete, if W is, here we want to delete X. Node is X, target node is X, we want to delete. Okay, and if, okay, for instance this one, we want to delete this one. Now let us see that case, this first case. If you want to delete this node B, this is a black node, right? And it has a right subtree. It has a right, W is a X siblings. Okay, then, and if this one is red, okay, then in that case, and on also this red has black children. We know that if it is red, then it has both children are black, right? Okay, and these black children are not even leaf. These are leaf level, but is not. These are not. Here is alpha, beta, gamma, delta, epsilon, phi. These are null values, like null type, all the loops. Okay, but we are considering A, B, C, D, E, F like this. Okay, then what do we need to do? We need to do a left rotation. Okay, so then left rotate 1x and then change its color. Oh, one thing that, for instance, one thing I forgot. So in order to delete, whenever we delete, when we go towards the down children to change color, but insertion we go up. Okay, for insertion we saw that we go with color or recolor in uncle level, parent level, or uncle level, or grandparent level if needed. But here we will change color okay, is either its own color, or it will go its children color or grandchildren color, down level. Sometime it will go nephew's color. You will check nephew color. Okay. Okay, so then in that case, for instance, W must have black children, W have black children, make W black, and then and PX, and then this PX as red. Okay, because W is red, PX cannot have been red. W is red, this cannot have been red. So then make a left rotation on PX. Then if you do make left rotation on PX, then siblings of X or the children of before rotation must be black, and then this is left rotation. So it will come over here, C will go over here, and then this B will be this is the complexity. It says, because now go to the other cases, case 2, 3, 4. Well, we did not have any case 2, 3, 4 yet. So we did not check the case 3, 4 yet. So I don't know it is. So this is the complexity. I remember that I could not keep my concentration. Okay. So there are slides, there are book. So let me tell you the situation. That case 1, if W is red, we want to delete X. Okay, not W, but X has a child. That is, if that is right child, and if that is red, then this is case 1. And now go to case 2. If this W is a black. Okay, so initially the first one was red, W was red, and this one is W is black. Then it has different situation. Okay, then it is recoloring. Then the third one, case 3, if W is black and W is the left, and W's left child is red, and W is black but W's left child. So we want to delete this, but still we are looking for children, grandchildren color. Okay, in this case we are looking this C color. If C color is red, then case 3, and now go to the case 4, is W is red and W's right child is red. If this one also red. Okay, and in this case it doesn't matter. So they put yellow, that means it is either can be black or can be red. So this is put yellow color. Then this is the situation. So they discussed actually 4, right? Here is 4. They said 4. In this slide says this 4 will cover all of these 8 conditions, but I know at least 6 conditions. I will not be able to explain this tonight. It will need a complete fresh lecture, an hour, to explain this. But what I did some research and then find some resources. One of the resources I would like to share you. Okay, I will give a link. Then whenever you have some cool brain, at least watch the video and then try to do something. And for the assignment, I will give you, I gave the assignment. It said illustrate with example, that either you write algorithm that covers all situations, or illustrate with an example that covers all situations. Either way you can do. Yes.
Do you think Sunday is a little soon to have all of it done though? Because like I looked at the assignment and it seems really long.
You need an extension?
Yeah.
How long?
Beats me. I just know that Sunday is a little too soon.
Let me see that our schedule for the inter schedule. Okay, let me see. Let me see. No, next month it will be too late. Let me see if I have another something conflicting. What is your next upcoming? We're in this week, right? We moved here, right? I didn't. We moved here, right? So then, if we moved 10th, we did here quiz. Then we need to move it here. Okay. One thing is that my target was if I can give 5 quizzes and 5 assignment, I will drop the lowest grade. But if I don't have time, if you ask me to push back, and then if I cannot give 6 assignment, then all 5 will be graded. Okay. So if you like to push it back, then there is a possibility that in 1 week there will be 2 quizzes. What in the consecutive weeks will we have 2 quizzes, or quiz 6 will be missing. What do you think?
We could just make this one due like Wednesday, so we have like the entire weekend, and then Monday if we need to ask questions, we can.
Okay.
Yeah, and then we can still
Okay,
do
that
this.
is doable. I can do then you said instead of 10, then make it 12.
Yeah.
Okay, that is doable. That's doable.
Well,
Okay. Okay, then actually, let me make it 13, 3 days, and then there is no deadline. Okay, without penalty, 13. But there is no more extended deadline.
Yep.
You understand?
Yeah.
That is good?
Yes, sir.
Okay. Okay, let us wrap it.